Good afternoon, everyone. Welcome to the problem solving session for course NOC 23 EE82. This is week 9, September 23rd. My name is Amit. I'm a PhD scholar at IISc Bangalore. Just a quick overview that what I've been doing in this course. So, in the week 1, we talked about the material classification of metals, insulators, and semiconductors in terms of their conductivity, the electrical conductivity, that is. And then we went in a basics of quantum mechanics like de Broglie wavelength, if you remember, lambda equal to h over p, where p is the momentum, h is the Planck's constant, and the Heisenberg uncertainty principle, which these are some of the bedrocks of your quantum mechanics. Then we saw something called the infinite quantum well. So by that I mean on the y-axis you have the potential Vx and V, and let's say on x-axis you have the position, and this is something like an infinite quantum well look like. So this is infinite level, right? And it has some finite width L, and we saw that when a particle is confined to this, it has quantized energy. This means it cannot have arbitrary energy levels, but only some energy levels are allowed. This is an asymmetric quantum well. Symmetric one will be, let's say, from minus L by L to L. Then we saw something called a finite quantum well. So again, y-axis you have your momentum, and so this is something called a finite or a potential barrier, let's say. So particle is coming, let's say, in this direction, and this is some finite energy potential V naught. So classically this particle can never be found on this side because its energy can never be higher than V naught. This is the energy, mind you. But we saw that in quantum world this is possible due to something called a tunneling probability, which obviously depends on the height of the barrier and the width of the barrier. This is the width of the barrier, let's say L naught, and there is some finite probability of finding the particle here. So this is peculiar to the quantum world. Why are we discussing that? Because essentially when we're talking about semiconductors, it's a lattice of atoms. They have their own field, and there's a potential energy associated with that. So we saw that we can model it using the Ronick-Penny model, and we had made some assumptions in that of the periodic potential, and we finally arrived at something called a band gap. That is, this is, let's say, the conduction band, this is the valence band. So only these above conduction band and below valence band are allowed. This is the forbidden gap. An electron cannot reside here. That's what we meant by band gap. And we also saw we can excite the electrons from valence band to conduction band, which can then contribute to the current. And we saw an entity called the effective mass, denoted by m star or m effective, right? This depends on the curvature. So I'm drawing the EC and EV as flat. They're not flat. In fact, if you draw in EK, E is your energy, K is your momentum. So they look something like this. So this is your EC, this is your EV. This curvature gives you the effective mass. Essentially all the quantum mechanical effects, right, which are always present in a semiconductor lattice, they can be confined to one entity called the effective mass, and thus we can, for all practical purposes as far as this course is concerned, we can forget about the quantum effects, right? And this effective mass, as I am telling, depends on the curvature of this of the conduction band and valence band. So conduction band will give you effective mass of electrons, valence band curvature will give you effective mass of holes. Then we saw that we can actually dope the semiconductor. That's the peculiar property of semiconductor. Metals conductivity is fixed, you cannot change that. Semiconductors, depending on what you are doping it with, if you are doping it n type, that is donors, you can have excess of electrons than the background, right? And similarly, if you dope it with acceptors, it becomes p type, that means excess of holes. How we determine that? So we can determine that by drawing something called a Fermi level. Fermi level is something where they're finding the probability of electron is half. So for intrinsic, this means no dope. So EF will be right at the middle. For, let's say, you dope it n type, which I'm denoting with green color, you will see that EF has shifted a bit towards EC. Similarly, if you dope it n type, which I'm drawing in pink or magenta color here, it will shift towards EV, like here, it will shift down. So that's, we can dope, and its position changes, and this is true only for a non-degenerate semiconductor, which means that EF minus EC, its mod has to be greater than or equal to 3 kT, because then some other effects come into the picture. And we saw then again some quantum mechanics was involved to arrive at the concentration of the intrinsic concentration Ni. What is the background? Hello, yeah, Vinod. Oh, I was muted, I guess. Sorry about that. Am I audible now? Okay, if you have any.
Yes, sir.
Okay, thank you. So I was just going through the summary of the previous week. We talked about material classification, that's conductivity based on conductivity, some quantum mechanical effects of de Broglie wavelength and Heisenberg uncertainty principle. Then I talked about the quantum wells. We had infinite quantum well where the if a particle is trapped here, its energy is quantized. And this is asymmetric well. Then we talk about quantum tunneling in case of finite quantum well or a potential barrier, let's say. Classically, a particle can never be found on the right side of the potential barrier if its energy is less than the potential barrier, but in quantum mechanical world it is possible, something related to a tunneling probability. Then we saw the how the all the quantum mechanical effects we assumed it to be a periodic potential, applied the Ronning-Penny model, and we saw that there is a band gap that originates in a semiconductor, and we can excite from valence band to conduction band by, let's say, shining some light or thermally also. All the quantum mechanical effects are condensed into one thing called the effective mass, which is given by the dispersion relation. Dispersion relation is E versus K, which I have drawn over here. And the curvature of the conduction band, it's not flat, this is an ideal picture. Curvature of a conduction band EC will give you the effective mass of electron, curvature of valence band will give effective mass of holes, and we can dope them n type on p type, and their Fermi level position changes and the concentration of electrons as holes naturally changes. Ni is the intrinsic concentration, which means you have not doped with anything, so Ni at equilibrium will be the same. So silicon, for instance, its room temperature is around 10 to the power 10 cm minus 3. Nc and Nv are some constants that again are derived. There are some Fermi during the Fermi solving the Fermi equation, right? And this concentration depends on temperature. For instance, at very low temperature, the dopants will not be ionized, so you will have very low background concentration of electrons and holes. If you increase the temperature, let's say at 100 degrees, at 200 Kelvin or something, they'll get ionized. So now the background concentration will be equal to the concentration of the dopants you have. Finally, if you increase the temperature even further, what's going to happen is you're going to break the semiconductor bonds and electron hole concentration will rise drastically. Finally, we saw that the doping can be non-uniform in the sense that, and this will give rise to something called the sloping band. So this is EC and EV. If there is some slope in potentials, that means there's some electric field, which we call built-in electric field. And now we talk about so having the electrons is just not sufficient, you also have to transport it. So how do we transport? We can transport by two mechanisms. By drift, this means there's an electric field and they'll move according to the electric field, because Vd, drift velocity, equal to the mobility times the electric field. Similarly, if there is a concentration gradient, the concentration of electrons is high on one hand and low on the other hand, what's going to happen is that the electrons will flow in one direction or the other, and total current will be given by the sum of them. Okay, and Einstein relation, by the way, links with the mobility mu and the diffusion constant d. However, semiconductor is not a thermal equilibrium, which I can do by connecting it to a battery. This means you are injecting some carriers, or you can shine light, which can generate electron hole pairs, and naturally some of them may recombine. So electron and hole, if they are freely available, they can recombine. We discussed all this in terms of a minority carrier diffusion equation. You are welcome to go through my previous videos on this, or Professor Naresh's notes if you are interested. Finally, we saw all these basics and we saw how a p-n junction is formed. So on the left side you have a p, right side you have a n. There is a concentration. There is a concentration gradient of electrons and holes, so they will diffuse. And depletion region is formed, which is used to form the then we saw depletion approximation to solve the Poisson's equation. And these are the key terms which keep appear: depletion width, peak electric field, stored charge, because remember there's a depletion region that will get formed here. So whatever charge you have of lattices, this is what we call the stored charge. And there's a built-in potential. So if you recall, it looks something like this. So this is the depletion region, this is p side, this is n side. So this is how we saw them in the previous sessions. Finally, we saw something called a quasi-Fermi level. So I'll draw the quasi-Fermi level here itself. So this is the QFP and this is QFN. Quasi-Fermi level happens when we have non-equilibrium, that is. So that can happen when you apply forward bias. Forward bias means P is connected to positive terminal of the battery. There will be injection of carriers and consequently the potential barrier will lower, and then the carriers can diffuse to the right because the barrier has been lowered, and they'll recombine there, thus completing the circuit, right? In the reverse also happens, the depletion region widens, the potential barrier gets increased, and that's usually denoted by something called the junction capacitance, right? Finally, we came to another type of junction is the metal semiconductor junction. So this is different in the sense that this is a metal This the dark one. This is semiconductor. So again you have a junction over here, and again they depend on the work functions. If you recall the work functions, this is the difference between the Fermi level and some arbitrary vacuum level. The difference in energies, that is. Key terms here we saw, this is also known as, by the way, as Schottky junction. We saw the barrier height, again the built-in potential, because if there is a difference in the Fermi level, the electrons can transport between metal and semiconductor. That depends. So the transport here is not by diffusion but by thermionic, and this is something called Richardson constants, which we studied. And we saw there are two types of contacts depending on the level of depending on their work function, that is rectifying contact or an ohmic contact. Both are important. And finally we came to the topics we have been discussing for the past 2 weeks, which is the MOSFET, metal oxide semiconductor capacitor. We saw its 4 regimes: flat band, accumulation, depletion, and inversion. So MOSFET is something that looks something like this. So this is your metal, this is your oxide rising sitting on a semiconductor. This is what we saw, and we saw that depending on the voltage that you apply on the metal over here, right, which we usually refer to as Vg, right, and let's say semiconductor is p type, so if you apply a negative potential to Vg, the holes will get attracted at this interface, right, and you have accumulation. If you apply negative potential, this will be depleted, you enter depletion regime. If you apply a high enough positive potential, gate potential, what you are going to see something called the inversion. A thin layer of electrons will be formed at this junction, which is what we call inversion. This means although the background is p type, but the layer that you are forming here is n type. It has inverted. So sometimes we saw a surface potential and the voltage drop across, so some voltage will drop because there's an electric field. All right, there's a capacitance associated here, Cox. Finally, we saw in the last session we saw capacitance voltage characteristics of ideal MOSFET, and we saw its two regimes in high frequency and low frequency. So if you recall, it looks something like this. This is for high frequency, this is the accumulation regime. Let me draw. So this is your Vg versus capacitance voltage, sorry, this is capacitance versus Vg. So I'm talking about the N MOSFET, and this is the high frequency regime, and this is the low frequency regime. This is what we had studied. So this is the depletion region. Here the inversion starts. Inversion, as we'll be talking more about inversion today. And we also saw in the last session some non-idealities, that is the metal semiconductor work function, there can be difference. So earlier in the ideal case we had assumed the work function of this metal and semiconductor to be same, which is not always the case actually. And there must be some trap charges here which can shift the threshold voltage. So this is this where the inversion starts, something we call the V threshold, VTH. Okay, and this is what we had seen, that this is how a MOS capacitor will look like. Right, we have assumed some assumptions there, and I have talked about the flat band, the accumulation. If you have a negative voltage, you have accumulation. Positive voltage, you have depletion. If you increase the even further, so you see here EF in the bulk is closer to EV. This means it's p type here. However, at this interface, EF is closer to EC. This means it's n type, and this is what we mean by inversion, that in the bulk it's p type, but on the interface it's n type. So there will be a sheet of electrons that will be residing here, and at the point at which this happens is known as the threshold voltage. So we have talked about this, so I'm not going to repeat this. You're welcome to go through the so this is the final summary. So this is how the LFCV, low frequency CV curve, and this is the high frequency CV, which I had drawn earlier. So this region is accumulation, and this region is inversion, this whole region is inversion, and this is depletion. Okay, right, and we had also talked about the non-idealities there, and this is the final correction that we came to. Phi ms comes from the difference in metal semiconductor, Qi comes due to the trap charges in the oxide, which you can see over here, and D is the depletion, which makes sense because we want to effectively invert it, so it has to be depleted first, and 2 phi f comes due to the factor of the inversion itself. This is the depletion charge, this is work function. So this I am just repeating them because we are going to use this extensively today. So that's that. If you have any doubts or comments till now, feel free to speak because we are going to start from today's session in a few seconds. I went fast through this revision because first of all it's a lot of content. Second, it's already there in the videos and you know that, so that's why I went it fast. Right. So now what I am going to do, we are going to start with today's session. So let's start. What is a resistor? So resistor means if you apply a potential difference between two terminals, the current is going to be determined only by them. So in this case, just assume this to be a water pipe. So left and right levels at the same level, so no water can flow. However, if you let's say tilt it such that V left is greater than V right, so potential here is higher. So what's going to happen? Water will flow from left to right. Vice versa, if the potential at right is higher, so water will flow from right to left. Transistor on the other hand is where a third terminal will control the current flowing between two terminals. So this is the first terminal on the left and the second terminal on the right. So however, third terminal, the middle terminal, is going to decide whether water can flow. So in this case you can see the water level is slightly higher, just higher than the level decided by the middle terminal. So in this case some water can flow. All right, okay. So what's going to happen, let me lower the barrier. So please recall the left and right are at the same. So left potential is, let's say, V1 here, V1 here, V2 here. It's the same as V1 and V2. The only difference is you can see the middle level has been lowered. So what's going to happen, more current, more water can flow. So by lowering the middle barrier, I can control the current flowing between left and right terminal. Similarly, if I raise the barrier, note again, left is at V1, right it as V2. So if I raise the barrier, what's going to happen, now no amount of water can flow. So just by regulating the barrier of the voltage level of the middle barrier, the height of the barrier in the middle terminal, that is, I can control whether water can flow. So water here is an analogy. You can assume them to be electrons and thus currents. This is what a transistor means. So this means transistor comes from two words, actually, trans plus resistor. This means trans means from the other side. This means some other terminal is controlling the flow between two terminals, two given terminals, here V1 and V2. Okay. Now there are two flavors of transistors that we have. So first is BJT, that is bipolar junction transistor. Other is field effect transistor. There are many field effect transistors, so we are just going to talk about the simplest ones. First, what's a BJT? BJT is often, you must have seen, is denoted by something like this, P, N, P or NPN. There are two flavors for that. So there are three terminals that you can see: collector, emitter, and base. So essentially, I'm not going to explain how it happens. So what's that? So these are the three terminals that you have: emitter, base, and collector. This is just a schematic for this thing. Okay, so what's going to happen is emitter injects the carriers into the base, and if the base is narrow enough, they can be swept to the collector side, and they can be collected. So in this case, holes. So holes will be injected from P to N. It's a PN junction. So you can see there are two PN junctions. First PN junction here, second PN junction here. There are two PN junctions that we are talking about here. Okay. So this is basically we have heard about PN junction diode. So you can say this is the advanced version of that. In a manner, it is. It's just that there are two PN junctions, so there are some peculiarities involved. The peculiarities are only due to the PN junctions, so nothing else is coming to the picture. Okay, so here it's determined by, let's say, your diffusion and drift alone. So whatever mechanisms that I just talked about during the revision thing, the diffusion and drift is only going to determine that what's going to happen, what will be the current and all, right? And there are other things which are not, like the area also matters of the base, collector, and emitter. So you can see that the collector is very wide here. You can see this is how it's grown. So first we P type, then you implant N type, and then you again implant P type. So right, the second type of transistors that we have are the field effect transistors. So just forget about this source and drain for now. So let me just draw the MOSFET for you. So how did the MOSFET look like? This was the metal that we had. This was the oxide. It was sitting on a semiconductor. So metal, oxide, semiconductor. Now compare this with this. This is the same except for these two extra terminals, source and drain. Everything else remains the same. So this is what we call the body also. It's the same as this. This is the body. So MOSFET, this is MOSFET. MOSFET and MOSFET are the same except for these two terminals, which are source and drain, which are n plus type. So as we recall, n plus will determine that it's n type semiconductor, but it's highly doped. P silicon means this is silicon semiconductor which is doped p type but moderate doping. Just please recall the notation plus here. All right. So if you recall that in MOSFET we read about one regime called the inversion regime, right? In this we read something called inversion. In inversion, what's going to happen? This is a p-type silicon. So what happens is there's a sheet of electrons in inversion that happens here. Now let's say we are in inversion. We have inverted this by applying some positive gate voltage greater than Vt. Remember, threshold is where the inversion happens. Strong inversion occurs, right? So let's say Vg is greater than Vt, and you have formed this sheet of electrons over here. Now what can happen? Now there's a sheet of electrons that is available here. Now if we apply a bias across source and drain, so let's say I apply drain equal to plus 5 volts and source let's say is 0. I'm grounded this, and let's say body is also grounded because this is a terminal. Let's not worry about the body for now. 0 volts and 0 volts. So now what you're doing, across a sheet of electrons are seeing this plus 5 and 0 here, so electrons will start to move. Okay, what's going to happen is that electrons will start getting attracted towards the drain. This current electrons will start getting attracted towards the drain, and you thus have a current flowing. But this is heavily based on the MOSFET. That's what I'm saying. The inversion, the accumulation, all those concepts, that's why we first studied MOSFET. And now we are applying the understanding of MOSFET, especially of the inversion layer of the MOSFET, so that now we can drive the current between source and drain. So why it's a transistor? Why it's field effect? Because remember, the field here I'm talking about is electric field. So remember we saw the electric field curves and the potential and so on in a MOSFET. That's why the field effect. The field is being generated by the gate here. Its effect is going to determine whether there will be inversion, accumulation, depletion and whatnot. Why it's a transistor? Because source and drain can only conduct, right? They can two ways, and then in accumulation or in inversion. But the current flowing in depletion, there will be very small amount of current flowing because there will be no electrons that are going to be available here. It will be depleted. So only depending on the gate voltage, source and drain can talk to each other. Source and drain can conduct. Hence, the current flowing between source and drain is being determined by the gate, and thus this is a transistor. And this is a field effect transistor because the amount of charge that's going to build up here is determined by the field, electric field that is being provided by the gate terminal, right? So in this slide we talked about why it's a field effect, why does this name come into the picture, and why it's a transistor, right? So this is just the very basics of it, and it's very very straightforward to understand if you understand the MOSFET, for which we have talked 2 weeks about, right? It's built on a MOSFET. We have MOSFET. Okay, so let's move forward. So there are actually two ways in which this can happen, right? One is an E mode, which is the enhancement mode. One is the D mode, which is the depletion mode. Okay, we're going to talk about it one by one. Okay, so this is the first problem that we have for today. The question says, for an ideal N-type depletion MOSFET, choose the correct statement. Okay, so what I have drawn here is the picture of a depletion MOSFET. Excuse me. Okay, sorry about that. So here I have the schematic of a N-type depletion MOSFET. Why? What determines the N-type? If the substrate is P-type, or the body that we'll say here, so there will be an N-type channel that will be forming. Just imagine the MOSFET. So all these concepts we are going to borrow over here, right? So this will be formed here. Now the difference the difference only here is between the P and N, right? So so the question asked is that what type of inversion layer is going to be formed. So first of all, if it's a P-type substrate, we know the inversion will be N-type. We have talked about it. So P-type substrate means inversion layer of holes. That's the first thing that we notice. Inversion here of electrons, sorry. So inversion layer of electrons. So this cannot be correct, this cannot be correct, this cannot be correct. So right. So electron inversion layer will be formed, right? Now when will the inversion layer be formed? So we know that this is a p type. So when Vg is greater than some threshold voltage, remember the threshold voltage comes from your let's forget about metal semiconductor work function difference and the your built-in charges. So it comes to, first it has to get depleted and there will be surface potential difference. So remember, minus qd by cox plus 2 phi f. So this is the ideal VTH that we have. So this has to come there, right? And that can happen only when we have positive voltage, so that we can, so that this gets depleted. It's determined by this, and we raise the potential here further so as to invert it. That from where this term comes. So this is from the inversion term, strong inversion. This term comes from the depletion, right? So only when Vg greater than VTH, then only we can have an inversion layer, right? Correct. So just a second, right? So this can never be correct. Okay, now only two options is there. Electron inversion layer is created for the applied bias greater than threshold. This is always correct, right? This is correct. We are more interested in this. At zero applied bias, what's going to happen? That means at Vg equal to 0, right? What's going to be the condition? So here comes the definition of the depletion layer. So till now I was talking about the generic terms. I did not talk about this term. What is a depletion MOSFET? Okay, so depletion MOSFET is the one in which let me say N depletion MOSFET is the one where VTH is negative. So if VTH is negative, so you can say why will it turn out to be negative? Because we have to apply some positive potential. QD is negative here, remember, depletion charge. So you'll think VTH is always positive. No, this is ideal, remember that. Actual VTH, if you remember, is something called V flat band minus QD over Cox plus 2 phi f. This is non-ideal. And V flat band, if it's negative enough, what can happen? This can shift the whole VTH towards negative side. So let me draw the CV curves again. So this is your ideal curve. C versus V. Actually, this is not ideal. So what can happen is that in the dashed I'm drawing this, it can happen something like this. So you can see here the VTH is here, VT2 let's say, and VT1 is here. So VT2 you can see it's negative here. This means even at zero gate bias you will have inversion. That is what we mean by a depletion mode MOSFET or a depletion MOSFET. So VTH is low enough that even if you don't apply any VG, so VG even if it's 0, right, 0 is greater than VTH because VTH is negative. This is what I have written here. So I'll not confuse and write it again. We remove this. So this is what we mean by a depletion mode MOSFET. So the correct answer is this. Technically this is also correct, but this is a more correct option. So if only one option correct, then we'll say this. Okay, so that's how we do it. Now I told you about the second MOSFET, which is the enhancement MOSFET. So enhancement MOSFET is just, you can assume your typical CV curve that we had, right? So let's draw this. So a typical CV curve used to look something like this. I'm drawing only LFCV, so just HFCV is, we are more interested in the VTH, that's where it's happening, right? So this is VTH. Note, remember, this is accumulation and this is inversion, right? So this I have drawn, remember, for an NMOS cap, right? But here we are talking about P-type enhancement MOSFET. So first of all, we have to draw the diagram for that. So let's do this in the green color. So they say it's, so this has to be N because we are taking P type, and this has to be P plus. Alright, and the symbol also changes. So the symbol is something like this, arrow pointing out. Okay, so this is the symbol of a enhancement type P type MOSFET. And how will the CV curve look like? The CV curve will, for an ideal PMOS cap, look something like this. So I'm drawing in green. So just the mirror image of this actually along the y-axis. So how it's going to look? So this will be the accumulation region. to lip here. So this will be the inversion and this will be the accumulation, and this will be with something called the VTP, let's say, okay, to determine to distinguish from the n type, and I'm calling this as VTN. This is the only difference that we'll have. So I've drawn the same both of them in the same diagram, so just to illustrate the differences. Actually it's let me draw it a bit properly, the curves. Okay, just a second. So it will be like this, it will cross over. Yeah, this is better. Okay, so what we can see here, an enhancement mode. So we have drawn a p-type ideal p-type MOSFET. Alright, so how will it look like? So we can see here is that the VTP, right, is over here, it's some negative value. So when will the inversion layer be created? So inversion layer, in order to create the inversion layer, so you have to be in this regime. So VG has to be somewhere here. VG has to be somewhere here, right? So what we say that, what will the whole inversion? So this is a n-type substrate. So n substrate, this implies a P MOSFET, and this will also mean an inversion layer of holes, because only when the bulk is n-type, then only the inversion layer will be of holes. So inversion layer of holes, so electron inversion layer cannot be there, this is not there, this is not there, so whole inversion layer will be there. But when VG, so we are talking about the magnitude, so when magnitude of VG is greater than magnitude of VTP, this value, so let's say this is -1 volts, so when VG is, let's say, -2 volts, so magnitude of VG has to be greater than VTP, only then the whole inversion will be there. Note, at VG equal to 0 they cannot be holes, because we are more talking about an ideal MOSFET here, so that ideality of MOSFET we invoke. So this is not true. This is, if this were true, this means it would have been a depletion type MOSFET, right? So what we have here is then, so inversion whole inversion layer is created when VG is greater than VT. So this is the correct option. So VG greater than VT. So usually just think of it this way: if the MOSFET is ideal, right, then this is the case. Then you should get an enhancement type MOSFET. However, if your MOSFET is non-ideal, right, then what you can have is a depletion type MOSFET. So there are different applications require different flavors. So these are the two flavors of MOSFETs that you can have: depletion or enhancement. All right. So I'll take a pause here. If you want me to repeat something or ask your doubts regarding the things that we had talked about in just 10 minutes, feel free to ask. Else we'll move forward with how. So now, till now, what I have been saying is the relation. I've been invoking MOSFET over and over again, right? Especially in terms of threshold voltages, and in this case, when I was talking about enhancement or depletion type, right? So when we move forward now, we'll not invoke MOSFET so much. So we'll just assume that the MOSFET knowledge has been there, it's present there. Okay. So now let's put our understanding of a MOSFET to, now we'll focus more on the source and drain. We'll obviously bias gate, but primarily we'll be interested in how does the current, what is the current flowing, how much electrons can flow between source and drain. So just for now, we'll assume that the silicon is p-type. This means this will be an n MOSFET. Okay, and we'll assume that we'll just assume that the source is at 0 potential, and also that body is at 0 potential. We'll just these are the two assumptions that I'm making for the or at least for the next hour or so. Okay, so let's just move ahead with that. Okay, just a second. Okay, so this is you can say the front view of this MOSFET, and this is the complete picture. This is a 3D view which is taken from the book Razavi. It's a very famous book. So what you can see here is that you can see this this gray layer, which is the metal. This is, by the way, called the width, which you see here. the width of the MOSFET denoted by W. This you see the thickness of oxide, you can see Tox. This what you draw is L drawn, okay, and you can see this sum of this region. So remember, this is a p-type substrate, so N plus P, right? N plus and P, and if you don't bias them or anything, you will always have a depletion layer. So what's happening here? Let me just denote it here. This is the N plus region. This is the P region. So if you recall, there will be a diffusion of electrons from left to right and holes from right to left, but this is N plus. So we recall that all the depletion will be on P side. There will be very much let's say there's order of magnitude difference in the depletion. So if it's here in microns, this will be nanometers here. So how will the depletion layer look like? So if I zoom in over here, it will look something like this. So this is your N plus, this is your P. So depletion layer will look something like this. This is your depletion layer. N plus will not be depleted at all, in fact. So that's what you see. The depletion is extending into this side. So this is the depletion that you can say. Or there's other way of saying it. Sometimes the implantation is not proper. So there are different ways of doing this. Okay, so here just think of it that there's some L effective that is there. Alright, so in this case, okay, it's not the depletion, it's actually when you're implanting, so diffusion will happen somewhat over here. Just forget about this. The only thing of matter to us is this L effective. This is the, or from now on, L effective and L drawn, I'll assume they are to be the same, and we'll denote it as something called L, the length of the semiconductor. Okay, this dimension, let's call it L, the length of the dimension. Gate is sometimes polysilicon, it's the poly that is noted here, and source and drain you can see. Okay, so MOSFET has three regimes of operation. First is the off state, second is the linear, and final is the saturation. So let's quickly, I'll just for the next 10 minutes I'll go through these. So what is the off state? So remember we had this threshold voltage over here, and MOSFET is off when VG is less than VTH or VT. This is the VT formula, the complete with all the trap charges of oxide and the work function difference. So you can see there's a work function difference 5 ms. So all the non-idealities, if you incorporate that, but you get is VT, and MOSFET is in off state when VG is less than this voltage VT. This VT cannot change because this is constant. This is constant Cox. Qi is whatever when you are fabricating them, Qi is fixed. Depletion more or less depends on the doping, so this is more or less fixed. Cox is fixed, and phi f is just your your surface potential for strong inversion. Remember that again. So this also depends on your material properties like the doping and whatnot. Okay, so all of these entities are fixed. They do not depend, by fixed I mean they do not depend on the gate voltage as such. Okay, so Vt for all practical purposes is a constant term. So when Vg is less than Vt, all right, it's off. Why? Because there's no inversion layer. If there's no inversion layer over here, and what is to flow? It's all depletion here, or let's say accumulation. So that's a different regime. We are not going there. We're interested only in operating this MOSFET in inversion regime. So when Vg is less than inversion, there's no inversion layer of electrons. So there's no point. So no current will flow ideally, right? So we have discussed the off regime. Now let's discuss the linear regime. What do we mean by linear? So by linear, this is the assumption. So Vg is greater than Vt. What this means is that there is an inversion layer. You can see this inversion layer in the dashed line, right? Of electrons. This is p-type substrate. So this is grounded. Source I have also grounded, and Vd is not 0 here. So Vd is small. Okay, Vd is small, very small value. Let's say 0.1 volts. So small that this is uniform. This inversion charge layer is uniform. It's a perfect rectangle, so to speak. And this is the length L that I have been talking about. W we have not drawn because only seeing the front face. So you see that W over here. All these, by the way, pictures are from your lecture notes. Okay, so now let's write the expression for Vg. All right. So let me do that. So Vg, remember inversion has already happened. Okay. So Vg, where it's going to go is first of all 5 ms, metal work function difference, plus the second term will be your the oxide charges divided by the capacitance, because voltage has to be there, right? And then minus Q depletion. Notice this depletion region in orange, in gray here. This is the depletion region. There will be a depletion charge over here. QD over Cox, right? Plus 2 phi F to invoke strong inversion, and plus the inversion charge layer that we have here, minus Q inversion over Cox. So this is the VG that we are applying is going to drop across these 5 regimes. Alright. Also we notice that the first 4 terms that you are seeing, this is the Qox that I'm talking about, is nothing but Vt. This and this. So what I can write here is this. Now Vg equal to Vt minus Q inversion by Cox. Alright. From here what I can get is Q inversion. The inversion charge is Cox Vg minus Vt. Q inversion is Cox Vg minus Vt. What will the current? Current will be, okay, so let me just write it properly. Q inversion is Cox Vg minus Vt. What will be the current that is flowing? Cox, remember, usually we report in per unit area, so hence this multiplied by area. So Q inversion we know, we'll put the form here, times the area. Area is W into L. What is the area? This is the width, this is the length, divided by tau. Tau is essentially the time taken by the charge carriers, electrons in this case, to traverse this length L. I can write tau as L over V, the velocity. What is the velocity? Electric field is there between drain and source, so let's call this V drift. If you recall, Vd is equal to mu E, mu n times electric field E, right? What is the electric field? Electric field is, assuming VDS is small enough, so we are assuming uniform electric field, VDS is small, so the drop here I can simply write as VDS by L. Electric field VDS by L. VDS is the potential divided by the length L. This comes out to be L square by mu n VDS. Let's write that, L square by mu n VDS. You rearrange all these terms, you rearrange all the terms, and what you will get is mu n Cox W by L Vg minus Vt times VDS. This is the expression of current which will get under these assumptions. So what we get, if I vary VDS, right, Vg I am fixing, so Vg is such that Vg is greater than Vt, and if I vary VDS, I is directly proportional to V. This is a resistor. So how will the current look like? Current will look something like this. So this is ID, this is VDS, I is directly proportional to VDS. It looks something like this. This is for something, let's say VG1. If I increase VG, again it should be higher than VT. If I increase VG, then what I'll get is something like this. Just a second. So this is increasing VG, VG increasing. So slope will get higher and higher. Why? Because if you increase VG, the current should increase with the same VDS. So you can get a family of curves. They will be all straight lines. This means this is ohmic behavior. Again, I write this here as well. This is ohmic behavior. Hence, that's why this is called the linear regime. Okay. What are the assumptions? That obviously inversion layer is there and VDS is small. So let's break that assumption now. So this is the second picture. In this now, again, we are in inversion. Vg is greater than Vt. You see, Vg is greater than Vt. But now, this is not uniform. Remember, we had a rectangular channel. This is not rectangular. This is a tapered channel. Or to be more technical term, is gradual channel approximation. So at any given point of time x, at any given value of x, right? Let's say here, it has a potential Vx. This was constant earlier, right? So Vg minus Vx is greater than Vt. So you go anywhere, inversion, you will always find inversion. You will find inversion here, 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 here. So Vg minus Vx is V channel of x at any given point of x is greater than Vt, right? This is one of the consequences when we have increased the VDS. Okay, why does that happen? So we have to see it, let's say here. Remember, there's a depletion region that will form here. I'll draw it in blue color. Depletion region will form between this, right? Even at zero bias, this is, let's say, the depletion region. This depletion is under the metal also, right? So total charge that we write was Q depletion plus Q inversion. So this is already playing a role. And if apply a positive bias to this, right? When we apply a positive bias to this, so this means we are reverse biasing this N plus P junction. So this will extend even further. This means you are increasing the. So why does this happen? This happens because depletion charge gets increased and the total charge has to remain constant, hence inversion charge has to decrease. That's why you get this tapered profile. Okay, and just like that, the Q inversion which we found out earlier, this time is just going to be a function of x. It will be Cox. Earlier it was Vg minus Vt. Now it will Vg minus Vt minus Vx. This Vx term is essentially due to that depletion region is also playing a role. It's significant now, and it's not constant across as a position of x. Okay, and again we invoke I equal to Q inversion times A over tau, right? So what's going to happen now? Q inversion is that, but what is tau now? Tau, remember, is length. So let's say the length here, we talk about this differential length dx divided by the speed v, drift velocity. I can write dx by drift velocity is nothing but your mu times c. So I'm assuming a constant mobility throughout the channel from here to here. Mu times e. What is electric field? Electric field is only over here. So I'll write it dvx over dx, right? So let's plug all these values here and you get this expression. You get this expression and you integrate this now. So you see one of the dx's gets cancelled, right? You take dx on the other side. So you integrate this term and what you'll get is, this is from the lecture notes. So I'm going to skip, I'm not going to derive this. So mu n Cox W by L, you will get Vg minus Vt Vds minus Vds whole square by 2. Okay, this is the term that you will get now. Okay, and again this is a square law. You can see it's quadratic dependence. Okay, so if you recall, the earlier it was looking something like this. The linear regime when Vds was small. Now it's a quadratic, so it will look something like this. I'm drawing the dotted line. Look something like this, quadratic. This is IDS versus VDS, and again if you have some other curves of different values of VG, it will be again be a different curve. So let's say for a lower value of VG, this will look something like this, linear regime and then the quadratic regime. So what happens here? That's the next part, something called the channel pinch off. So let's say you have increased VDS even further, right? VDS large enough so the channel gets pinched off near drain. What do I mean by that? This is the expression, remember? Now what I'm going to do is Vx, the potential here, remember it's dependent on Vd, right? So Vx, so this inversion, let's make it equal to 0. There's no inversion here because depletion charge is sufficient at this junction. If I make it equal to 0, then what I get, Vx equal to Vg minus Vt. What is Vx? So all this Vx just at the drain. Vx is nothing but Vds in this case. So this is equal to Vds. Assuming the boundary case when the channel has just started to be pinched off. So the Vx will be nothing but Vds. The Vx is nothing but the potential at this point. At this point. What is the potential at drain? Vds, right? So Vds equal to Vg minus Vt. The channel will get pinched off. So how does the channel actually look like? Channel looks something like this. So this is your normal operation. So at pinch off, draw it again. At pinch off, channel looks something like this. So this I am drawing at Vds equal to Vg minus Vt. So this is your channel. So this will come, and this will get like this. So this is a channel of electrons, and I'll also do the depletion charge over here. This is a depletion layer. Okay, so this is your depletion layer, and in the red we have our channel. This is our channel of electrons, inversion layer, that is. So at this junction, what's going to happen, all the charge is being contributed by the depletion layer, and if you increase the VDS even further, let's say you increase VDS greater than VGT, so this channel will keep on shifting to the left, right? So let me draw in this color. If you increase the VDS even further, it will look something like this. So this corresponds to VDS greater than VG minus VT. Let's call this VDS1, right? Remember, we're not changing the VT, we are not changing the VG, sorry, and we're just modulating the VDS, because remember, transistor, the third terminal is gate, that decides the inversion layer, correct? But VDS, the other two terminals, we want to flow currents between them. So let's not change the VG, because we are interested in ID versus VD. That's the plot we have been drawing. So what's going to happen? So the thing that's going to happen, if the channel has been stopped, the current cannot increase anymore, right? The current cannot, because if you recall the charge expression, right, Q inversion was responsible for the charge that is flowing. You'll see that Q inversion has come out to be 0. Actually, it appears it to be 0, but there is a very small width, only a few nanometers, because the electrons that are coming from here has to pass to the drain. So it's a few nanometers, but essentially is saying is that the Q inversion is effectively non-existent, right, at this junction, but the flow will be there, right? So what's going to happen is that now the charge cannot increase any further. So if you, because remember the current expression that we had, the current expression, where was it? Yeah, something like this, Q inversion into A over time, right? So Q inversion into area over time. So now it cannot, so only the charge that is coming over here, that only can contribute, right? No extra, so here the charge is not this, so I cannot contribute. So any marginal, so I'll write marginal increase, marginal current increase is no more. So the current cannot increase any further. This is what we call, this is also known as, by the way, as saturation. The current has saturated. So remember, we draw two regimes earlier, linear, then we had a quadratic regime. After some time it reaches peaks and it saturates. This is ID versus VDS for a given VG, I'll again repeat that, right? So for different VGs it will look something like this. So it might look something like this. And that is the complete picture that I was talking about. So this is the linear regime, this one, and the quadratic thing that you saw was here. We had the quadratic expression which is written over here, this thing we had derived this, okay? So this corresponds to the red regime, and this is here we get saturated. This is the saturation regime. Here the current has flatlined. Alright, so this is the complete picture, and obviously please note that all of them, for different VGs this will be different, because ID you can, and the other way of seeing is that when you increasing this in this direction, inversion charge increases. For a constant VDS, inversion charge is increasing, and thus a current should also increase because there are more electrons to be transported, right? So you see this trend. However, all these blue curves are for VG greater than VT. So let me draw one more line here, VG minus VT equal to 0, and this would mean no current ideally. This is a linear scale, by the way. Okay, this is the complete picture. This is the diagram you see over and over again. So linear regime, quadratic regime, and the saturation regime. And what is this point of saturation? This point of saturation we calculated was VGS minus VT, pinch off. otherwise known as channel pinch off. Okay, so now we are equipped with all the information that we have about the MOSFET, and now we can start to solve the problems. Okay, so I'll wait for a couple of minutes in case you have any doubts, especially about the pinch off. Sometimes it can get confusing that if the channel is pinched off, how are the electrons even flowing, or how does the linear regime, when does the linear regime end, when does the saturation regime start? So all these things, so if you have any doubts, I'll just stay here on this slide. On this, we'll try to explain it. I'll try to explain if you have any doubts using this plot. All right, so I'll take a pause and let me tell you, let me give you some time to absorb this and ask a few questions if any. All right, then let's move ahead, and now it will be mostly numerical. So the theoretical part of this class is more or less over. We'll have some other concepts like channel length modulation and subthreshold slope towards the end, but for the most part it's done. Okay, so this question asks for a long channel MOSFET. Okay, this term has come now, long channel. We'll visit this in another 45 minutes or so, but long channel, let's say we are talking about ideal. What happens when it's a short channel, we'll see in a bit. Let's assume this, we're talking about an ideal MOSFET beyond pinch off. So beyond pinch off, we know we are talking about the saturation regime, that is this, after this dotted line, to the right of this dotted line, the saturated drain current varies as. So we are required to find that how does the saturated drain current vary with VGS. Okay, so this is the expression that we had seen after saturation. So this is actually from the square law, right? And we are required to find when does it saturate. Okay, so there are two ways of doing it. Actually, you can differentiate it and try to find out its maximum. That's one way of doing it. We differentiate with respect to VDS ID, so we differentiate with respect to VDS and try to find out its maximum. So let's do that. So we'll say del ID by del VDS equal to 0. You want to find the maximum of this square law. Okay, so let's do that. It will be mu C ox W by L. So VGS minus VT is a constant. It comes out times 1. Differential of VDS with respect to VDS is 1 minus VDS square by 2. So this will come out to be 2 times VDS by 2 equal to 0. This gets cancelled. All these terms are non-zero, so we can skip them. So VDS comes out to be VGS minus VT. So this will peak at VGS minus VT, and this is what we want, VDS sat. So after this it becomes saturated. It has peaked and it will saturate at its peak. So after this, how does it look like? So let's put VDS and we call it VDS sat. Let's put this value here. So it comes out as, we call it as ID sat now, mu n C ox W by L VGT. This term is sometimes also written as VGT, VGS minus VT, and I call this VDS sat minus VDS sat whole square by 2. So this will turn out to be mu n C ox W by L. So let's put the value of VDS sat as VGT. So this will be VGT minus VGT whole squared by 2. So mu C ox W by L VGT whole squared by 2. This is ID sat. And this fellow is ID sat, which is what we are required to find in this problem. Saturated drain current varies as, so all these three are constants. In fact, we cannot change them. So it depends only as VGT square by 2. VGT is VGS minus VT. Remember this. So it depends as the square. So this option is correct. And you can also see this dotted line that we had drawing here is ID with respect to VGT. So the dotted line that you see, this line, this is essentially your, this gives an idea, ID versus VG. Remember, VGS is increasing here, so this dotted line, it must come out to be a parabola. Say, because we are plotting these points only at the onset of saturation. Another way of seeing it, there's different ways of seeing this plot. So once at saturation, it must be a perfect parabola, and thus it has to be a square dependence. So hence VGS minus VT whole square. Alright, the key thing to note here is that we're talking about a long channel MOSFET. For now, we have not talked about it, so we'll talk about that's an ideal MOSFET, and this is beyond pinch off. So beyond pinch off means we have entered the saturation regime. So that's the right of this square line, right of this line, which is saturation. You can see the current is flat line, and we just saw what is the square law, found out its maxima, and we say it saturates there, and found out that the value, corresponding value of VDS at its saturates, so known as VTS sat, which is VGS minus VT. Okay, so that's the first problem that we have. Now the second problem that's asked here is that given below are the two statements related to current, ID is your drain current, in conventional PMOS and NMOS devices. So again, when we say conventional, I'll assume first of them to be ideal. Okay, that's an assumption that I'm making. So that long channel assumption I'm making again. Okay, then is statement 1 asks is that drain current of PMOS device is greater than drain current of an NMOS device for a particular VGS. Second statement is mobility of a PMOS device is less than mobility of the mu-n device at the interface. Okay, so let's just investigate the first statement. So it says ID drain current of a PMOS device. So let me write ID PMOS. It will be mu P C ox W over L. So what happens is that is PMOS, all of these things are negative. So we just put a like this. Nothing changes except you just put a mod on every term that you see. Okay, so so what, wait a second, where are we? Yeah, okay. So so it asks us that this is ID PMOS, so let's write ID NMOS. It will be mu n C ox WIL VGS minus VTN VDS minus VDS whole square by 2. So what I'm going to say here is something like this. So this is my metal oxide semiconductor. This is your source, this is your drain. So when we're talking about PMOS, so this will be, sorry, NMOS, this will be N plus, this will be P type. This is your metal. On the other hand, so this is your oxide again, this is your metal, right? This will be P plus, and this will be your N type substrate. So again, this is your source, this is your drain, or metal or gate. This is the same thing here, right? Okay, so VDS I am assuming same for both, because let's say we are applying the same potential to both of them. VGS I'll also assume to be the same. Okay, so the only difference that I'm going to have is first of all this term VTP and VTN. So the only two terms, so I'll write this, that assume VDSN equal to VDSP and VGSN equal to VGSP. So this is P, yeah, this is also P, this is N, and this is N. So all these terms are irrelevant. The only terms of significance, of relevance to us rather, are this VTP, VTN, mu P and mu N. Okay, so first let's talk about mu P and mu N. This is the mobility. So as it happens that mu N is greater than mu P, and you can think of it intuitively. So what is holes? Holes is just the absence of electrons, right? So let me draw a lattice here. Okay, so this is the, let's say, silicon lattice that we have, right? And so electrons, will be electrons that are so we draw the bonds also just to illustrate it more properly. Okay, so an electron is bound here, so only when electron leaves there will be a hole. For hole to be transported, there has to be another hole, correct? So if a hole has to be transported, let's say over here, soul, if it wants to come over here, that first of all electron has to leave here, correct? This is, among others, is one of the many reasons that the mobility of hole is usually lower than mobility of electrons, at least in the silicon semiconductors that we are, and the NMOS or PMOS device that we talk about here, right? So at the interface, at this interface where you will form an electron gas or an electron layer or a hole inversion layer, right? So in this case, what happens is that mobility of a PMOS device, right, mu p is usually lower than mu n. So this is true. This statement holds true. Okay, right. If this is all true, and let's say we just assume for, I mean, VTP and VTN are actually different. They're not the same. If you look at the expression for the VT, right? So VT, if you recall, something was phi ms minus q ox by c ox, the trap charges, minus q depletion over c ox plus 2 phi f, right? This was the expression. Q ox is usually we don't control whether it's PMOS or NMOS. Phi ms is also the same for both of them. Let's say depletion and phi f, 2 phi f you can control depending on the. So let's say these three terms are same. Q ox is still different, right? So VTP is slightly different. VT for P and VTN is slightly different. But mu P and mu N are the things that we are focusing on here. So if mu P is less than mu N, assuming VTP and VTN are same, so only this we can write that ID PMOS must be less than ID NMOS. Again, I am assuming that the threshold voltages, since the question is silent about it, right? So we'll assume the threshold voltage is the same, VTP equal to VTN. Then I will depend only on the mobility, and the mobility of electron is higher, so the drain current of electron should also be higher, right? So statement true in that sense, under that assumption, becomes false. The drain current of NMOS is higher. So first is false, second is true. So give us this answer. Again, I'm saying VTP and VTN that I'm assuming. It's not the case usually. It's more often than not. But let's, for the sake of this discussion, where we are focusing only on the mobility here, we'll assume them to be the same, because the question itself is a bit silent about that, because we have to know the nature of oxide charges, which are usually positive charged. Okay, so that's the case. Okay. Right, and also second thing which I should have pointed out early, actually, when nothing is given, we usually take, we are talking about the saturation current, but here I had written the square law. The discussion will not matter because VDS square by VDS P equal to VDSN we have assumed, but just to keep in mind, if nothing is given, we just start with the saturation current. Other things will also change definitely. Why I did not? Because it's the more truer picture. So this expression encapsulates the linear regime, the square law regime, the gradual channel, in which the channel is gradually, it is not pinched off, and if sorry, just a second, if S1 is less, then what would be, if S1 is less, yeah, if S1 is less, okay, so you are asking, if let's say the question says this is less, this was also given to be less here, then we would say S1 is true, because then it would be true. S2 we have established is true, and in fact the reason that is because you assumed VTP equal to VTN. So if there were in a hypothetical question, let me use a different color for that. So if this were less here, let's say this was less than here, then first would be true, second would be true, and second would be correct explanation of one. Why? Because we assume VTP equal to VTN, then only it's correct, right? So that's the answer. Is it okay, Vinod? Vinod, can I go ahead? I mean reason. Yes, reason S2 does explain it correctly, because remember in this expression, COX we are assuming for both of them the oxide layer is the same, the thickness and everything is the same. WL again I am assuming it is the same, width and length both of them, so this is L for both of them, Ln equal to LP. I've also assumed that the bias that we are applying is the same, and if I assume VTP equal to VTN, then this whole square bracket term vanishes. It is the same for both of them. The only term that is different between the expression for currents is only the mobility, mu. So if mu is different, I is different, because rest all of the other terms are constant. So S2 explains it correctly because there is no other variable that is left. So it's like saying y equal to mx, or I should say y equal to kx. All of this is k. This term is x, this term is y. Y equal to kx. K is a constant, so y depends only on x and nothing else. So if x is changing, y should change. If x is changing, this means mu n and mu p. If mu n is greater than mu p, then multiplying with a constant does not change the nature. So then ID NMOS will come out to be greater than ID PMOS. Yeah, VTH I am assuming that the same for them. That's the assumption that I'm making. I've written, I know they're not the same. For the sake of the discussion, I am saying they are the same here, because even if IMS, the depletion charge, and 2 phi f, you make it the same, QX, the nature of QX is not the same, because the signs are different essentially. That's what I mean to say. Hopefully we'll in the next session or somewhere this problem should come up again, or if it doesn't, we'll solve a problem in which this problem arises, where VTP is not equal to VTN, and then maybe we can revisit this question. Okay, so the next problem asks, this is from GATE 2008, 15 years ago. The drain current of a MOSFET in saturation regime is given by ID equal to, we solve this, it's a square dependence where K is a constant. The magnitude of the transconductance is, so we have ID equal to this, and what is transconductance? So transconductance comes from two words, trans plus conductance. Okay, as I have been saying that, so 3 terminals, right? I'll draw a very picture which is not drawn, just to illustrate my point. This is source, this is drain, and this is gate. So we want the current flowing between source and drain. So what will be the resistance? Let's say it RST. It will be del VST over del IST. The inverse of this is called the conductance. So denoted by G actually. GST will be del IST over del VST. This is your 1 over RST actually. So this is the conductance. What does the word transconductance? So this is conductance. This term is conductance. What do we mean by the term transconductance? So which I'll write here. So transconductance, as shown, it's noted by GM. Is denoted by GM, right? And it's given by the expression. The nature will remain the same, right? Del IDS, but the varying thing that we are doing is VGS. Why the subscript, why this term S? Because we are measuring everything in terms of source. Usually what we do is that we keep the source grounded, or the reference, right? So this is usually grounded, and we measure everything, so hence VGS, VDS, everything with respect to the source. So So this is what the transconductance formula looks like. We are measuring the conductance, but not between the two terminals VD and VS. The current we are measuring here and the voltage we are measuring here. Hence the term trans comes into the picture. Okay, so there's nothing to do now. We just put this formula, del K VGS minus VT whole square divided by del VGS. So we differentiate, K is a constant, it comes out. We differentiate the other term, so it comes out to be multiplied by 2 VGS minus VT, and then del VGS minus VT over del VGS will be 2K VGS minus VT times del VGS over del VGS is 1 minus 0. VT is a constant for VGS, so 1 minus 0. This turns out to be 2K VGS minus VT. So this is the GM that we are interested in. 2K VGS minus VT, which is this option. Let me see. Yeah, this is correct. 2K VGS minus VT. So this is a very straightforward problem, and this nothing much to explain here except for the concept of transconductance and its difference what we mean by conductance. So this term that I talked about here, conductance or the resistance, this term RST, we'll see in today's session it comes in a different form. Okay, so sometimes it's also written as R naught. This term R del VD over del I, del VD let's say over del ID. Okay, transconductance is actually a very important parameter of a FET, because because you can see that it's directly related to what is your K, constant K. K is your essentially coming from your device parameters W and so on, right? And it also depends on VGS. VT is usually we do not have much control over. VGS is the bias that we are applying. So GM is essentially a good reflection, I should say, of your drain current, right? Of, let's say, when you're comparing two devices. So that's why this term is important. Okay, the next problem we have, consider an ideal long channel. So again, this term ideal and long channel. So ideal, and when we say long channel, we just assume it. So these two terms actually go hand in hand, ideal and long channel. So, and it's an N MOSFET, and we are given mu n C ox W by L and so on. So we are given drain currents for two different VGS. Okay, wait, we have to find drain current for this VGS and this VGS and this VDS, sorry. Okay, so we know, I know only this expression. So from this expression I can go to linear regime, the square law, as well as the saturation. Okay, so first thing we want to know which regime are we in. So first we have established that it's an ideal MOSFET. By ideal here I mean it's a long channel. Second is, what regime are we in, what region are we operating in. How do we do that? We must first check whether it's even inverted or not. So VG greater than VT, is it true? Let's check. So VG, what's VG? VG is 0.8 and VT is 0.4. So this is true. So VG is greater than VT. This means there is an inversion. So there will be a inversion layer of electrons. This is an N MOSFET. So this must be happening on a P-type substrate. Hence this is given mu N. Right. Second thing we check is whether VDS is greater than VDS sat to determine whether we have entered saturation or not. This means inversion is there. So this formula is valid. This formula is valid only in inversion. Right. That's it. If it's inversion, this formula is valid. But we must, second thing we want to check whether this has entered saturation or not. So in saturation, you know that VDS has to, VDS has to be replaced by VD sat because the channel has pinched off. So let's say VDS is given as 2.5 volts. Is it greater than VDS sat? VDS sat is, remember, VG minus VT. So VG is 0.8 minus 0.4. So 2.5 is greater than 0.4. This is true. This means we are in saturation. Okay. So this means this MOSFET is operating in saturation regime and we want to find the ID. So let's do that. So if we are in saturation, this means we have to replace VDS with VDS sat. Let me write this. Since in saturation, replace VDS with VDS sat. So let's do that. So the expression will become ID equal to mu n C ox W over L. Again I'm writing this term as VGT to save some space. So VGT times VDS sat minus VDS sat whole square by 2. So mu n C ox W by L. VDS sat is nothing but VGT. So I write VGT times VGT minus VGT whole square by 2. So this terms mu n C ox W over 2L VGT whole square. Now just the numbers. Mu n C ox is 0.18 milliamps per volt square. W by L is 8, so there's a by 2 here, by 2. VGT, we determined it's 0.8 minus 0.4, so 0.8 minus 0.4 squared. So this will be volt squared. Volt squared will get cancelled with this, and I'll get 0.18 times 4 times 0.4 squared milliamps. So let me find my calculator. So it's 0.18 times 4 times 0.4 is 0.4. It's 0.1152 milliamps. It's coming out to be 0.1152 milliamps. 0.1152 milliamps, this option. Okay, so that's how we solve this problem. The main the main takeaway that I want you to have from this sorry, one second. Can you see my screen? My wire, just one of the wires got disconnected. Can you just confirm if you can see my screen and my cursor moving? Am I audible? Yes. Okay, good, thank you. So the question is, if VDS is less than VD sat, then would it be linear? No, not necessarily. Not necessarily, Vinod. See, it will follow this regime. Linear happens only when VDS is, so you see, it will follow the square law. So VDS is less than VDS. Let me use a different color. 1 second. Because we are dealing with something that's not directly not stated in the problem, so I'll write it in this portion over here. Okay, so if VDS is less than VDS sat, this means we are in square law regime. So by that, what do I mean? You remember, recall this diagram of ID versus VDS. Linear, then your square, and then your saturation. So this is from where the saturation has started. This is saturation. So I can be either here or here. So this is the linear regime, and this is my square law regime. So when VDS is less than VDS sat, you can either be in square law or in linear. Some people, some books rather, however you may want to put it, they club linear and square into linear regime. I will not say that. I will not say that term, that this whole thing is linear. No, it can be approximated as linear, yes, but it's not linear. Linear is only when VDS is very small. Okay, when VDS is large but not large enough to be VDS sat, then you enter into a regime which is neither linear nor saturation. That's why we call it the square law, the gradual channel approximation, which we saw today. So I'll not say that it's strictly linear because I don't know the value of VDS. If VDS is very small, let's say they say VDS less than VDS sat, yes, then I will safely assume we are in linear regime. But if not, then no, I'll not say that. Okay, right. Okay, so let's go ahead. Oh, does that answer your question, Vinod? Okay, I'll, I'll I'll just go ahead. Say zero point 0.1 VD, say 0.1 VDS sat. Um, so 0.1 VDS sat, no, in this problem we have zero point 0.4 as VDS sat. Yeah, so we remember VDS sat was 0.4. So if we have VDS equal to 0.1, then yes, I can say that it's linear, it's very close to linear. Yeah, because essentially what I have to compare is these two terms. Okay, if VDS by 2, how does the first term, which is the linear term, compare with the second term? Okay, so let's do that exercise here itself. When do we say the linear regime has sat in? So there has to be some we have to put in some number. So this number is VGT. So let's say when the first term is 10 times the second term, then only I'll say it's in linear. Okay, so VGT minus VDS. Okay, so this will turn out to be 5 times VDS. So I can say when VGT is equal to 6 times VDS sat, you have to figure out a way of, because there's no hard and fast rule when do we say it's linear. So I am assuming it's 10 times. Some people say that when first term is 5 times the second term, we can ignore the second term, right? Then only the first term will dominate. So that's that. In this case, if let's say VDS equal to 0.1, let's put this number. So first term will come out to be then 0.4 times 0.1. First term will come out to be 0.04. This is VGT times VDS, and VDS square by 2, right? VDS square by 2 in that case will turn out to be 0.1 squared, so that's 0.01 divided by 2, 0.005. Yeah, if that is the case, because 0.04 is much greater than 0.005, there's 8 times the difference, then yes, I'll say it's a linear regime. Yes. So for 0.1, let's say VDS equal to 0.1, we are in linear. So 0.4 volts VDS. So 0.4 volts VDS is VDS sat. So then we'll say we have entered saturation. At 0.1 VDS, we'll say that at 0.1 VDS, we'll say we are in linear. At 0.4 VDS, at 0.4 volts VDS, we'll say that we have entered saturation. And let's say in the middle, we'll say we are in the square law regime. So that's how I'll put it for this problem. Okay. I'm not able to understand your question. The above formula is valid. This square law is valid in linear regime and in saturation regime and in square law regime. Only in saturation regime you just have to check whether, which I did here, which regime. So that's why I'm writing this whole process. First, the ideal MOSFET. Second, I find it out which region it is in. First, I checked whether it's in inversion. It turned out to be true because VG is greater than VT. Second, I compared VDS with VDS sat. So if VDS is greater than VDS sat, which in this case is true, then I said it's in saturation. When in saturation, I just change this formula. When in saturation, that's why I write, since in saturation, replace VDS with VDS sat. So because I remember only this formula, no other expressions. If it's in linear, I drop this quadratic term. If it's saturation, I put VDS equal to VGT. That's it. That's the only change that I need to make. So okay, right, got doubts? Right, moving forward. So in this problem we are given ID versus VGS. Note, not ID versus VD, ID versus VGS. By the way, this kind of plot, ID versus VGS, is also known as transfer characteristics. So you may see this term. transfer characteristics, ID versus VGS. Okay. So it's determined experimentally for an n channel MOSFET are given below. The width and length W and L are given. VDS is given as 0.1 volts. Okay, VDS is given as 0.1 volts and Cox is given. So we are required to find the mobility of carriers in the inversion region. So again, first thing is whether the chat is ideal or not. So I'll assume it to be ideal first of all. Second, the question itself says mobility of carriers in inversion region. This means the channel is inverted already. That's why they are asking this problem. Okay, now what I need to do here is so I need to invoke a formula, this, because this is the only formula I can remember. So this is mu n because it's an n channel MOSFET, and I just need to figure out, I'll put the terms in this formula over here, right? And I'll try to figure out whether I can find mu or not. Okay, so let's just take these 2 points. So let's call this point 1 and let's call this point 2. Let's try to see if we can find out the numbers which are unknown. So I can simply write that ID1 equal to mu n Cox W over L VGS1 minus VT times VDS minus VDS whole square by 2. VDS is same for 0.1 and 0.2. So what is the value of ID1? ID1 is 25 micro. Mu n we don't know. Cox we know is 8 into 10 to the power minus 8. W by L is 10 by 1. VGS1 is 1.5. You see this point, 1.5 minus VT. VDS is 0.1. VDS is 0.1 minus 0.1 whole square by 2. I made an assumption here. The assumption that I am making here is we are not in saturation, because if we were in saturation, then I have written VDS equal to VGT. So right now this is my only assumption. Now I can also write the second expression for ID2. So ID2 will be mu n Cox W by L VGS2 minus VT VDS minus VDS whole square by 2. So ID2 is this point, so that is 65 microamps equal to mu n. Cox is 8 into 10 to the power minus 8 into 10 by 1. Value here is 2.5, so 2.5 minus VT. VDS is 0.1 minus 0.1 square by 2. So what I do is, now see the terms which can be cancelled. So I need to find mu n, but what I don't know is this VT, correct? Okay, so how do I solve this? Hold on a second. Okay, if I divide these two, 1 divided by 2, right, then what's going to happen, or I can even subtract in fact, because this term, yeah, this term is common. See, this term is a constant for both of them. Yeah, if I subtract, I'll be fine. So I'll do 2 minus 1. We do 2 minus 1, so I get LHS will be 65 minus 25 microns equal to, this term is common, remember, mu n, and this term is common, so I can take that out common. 8 into 10 to the power minus 8 into 10 square bracket start. First term is, so 2 minus 1, it will be 2.5 into 0.1 minus VT into 0.1 minus 0.1 whole square by 2. So this is from the ID2 term. From ID1 term it will be 1.5 times 0.1 minus VT times 0.1 minus 0.1 whole square by 2, and we close the square bracket. So VT, this term and this term gets cancelled. Okay, so what I'll get is 40 microns, sorry about that, 40 microns equal to mu times 8 into 10 to the power minus 7. Minus 8 into 10 is minus 7, so I'm writing this over here now, into, this will be 0.25, this will be 0.15, so this will be 0.1 into 0.1. Okay, so we now do this. I'm doing this here. So mu n will turn out to be 40 micron divided by 8 into 10 to the power minus 7 into 0.1. So this will be 40, this will be 5 into this is minus 7 minus 8 over minus 6, 500. Okay, units I should have taken, so units are sent cm minus 2 because all other thing is in, yeah, this microns get cancelled, cox is cm, yeah, so only this term survives, cm minus 2. So this is cm centimeter square per volt second. So this is 500 centimeter square per volt second. This is a typical value for the electron mobility in silicon MOSFETs. Alright, so what we did here is a very straightforward expression. The mobility was required to be we are required to find the mobility, but we were given ID versus VGS, which is also called the transfer characteristics. We just wrote the expressions and we saw we need to find mu n, subtract the 2, and the rest is just mathematics, nothing of significance over there. The second problem in this set is, so this is we established to be 500. Now we are required to find the threshold voltage. Remember previously I was confused because you have two unknowns here, mu and Vt, correct? So we subtracted and there were two unknowns, mu n and Vt, and two expressions. So we found out the first unknown mu n. Now we just need to find the second unknown, which is Vt. So I'll use this expression again, but I'll use just at the point 1. So I'll write ID1 equal to mu n Cox VGS1 and so on. So ID1 is 25, mu we know is 500, Cox we know is 8 into 10 to the power minus 8, right? W by L is 10 over 1, VGS1 is 1.5, Vt we don't know, VDS we know is 0.1, and this is 0.1 whole square by 2. So what I'm assuming here, we are not in saturation. That's the assumption in the previous slide also. I'm assuming not in saturation, and we'll also confirm this this assumption once we find out the value of Vt. So let's quickly do that. So this will turn out to be 25 into 10 to the power minus 6 equal to this 500 times 8 is 4000. So 4000, this will be 4 into 10 to the power minus 4, because minus 5 and this 10 will become minus 4, and the rest of the term would be 1.5 minus Vt times 0.1 minus 0.01 by 2. Okay, so this will be 1.5 minus Vt times 0.1 minus 0.005. This will be equal to so 25 by 4, and there's that term also, 0.0625. So this is 0.0625. So from this 1.5 minus Vt into 0.1 is coming out to be 0.005. Just a second, 0.01, yeah, so 0.0675, and 1.5 minus Vt will come out to be 0.675. From this Vt will come out to be, so this was 1.5 minus 0.675 is 0.825. Vt we have obtained is 0.825 volts, assuming we are not in saturation. Remember, let's now confirm this assumption. How do we confirm this? We find VDS and we compare with VGT. VDS is given as 0.1 volts, VG is given as 1.5, let's say over here, excuse me, and Vt is we obtained as 0.825. So this is 0.1 volts and this is 0.675 volts, and you can see that VDS is not greater than VGT. VGT is greater than VDS. This implies assumption was correct. So remember, we had assumed it to be not in saturation, and this assumption we see that it is indeed correct. Okay, other thing was intuitive. Why do I say that? I say that VDS was very small. Just in the previous problem, Vinod asked that what if VDS is zero point 0.1? So VDS, that's how I saw that. If VDS is very small, zero point 0.1, usually it's not in saturation. We are operating in linear regime or the square law regime. So I just assumed that, and this is actually the formal way of doing that. That's how I did that. Okay, so yeah, so let's go ahead now. Okay, so the next problem is the transconductor of n-channel MOSFET is found to be this when measured VDS and VT is given. So we are required to find the transconductance parameter. Okay, so all right, so this transconductance is different from this transconductance parameter. So just please don't be confused. This is just a parameter. It's just a constant that comes in the expressions. Okay. So as always, I only know one expression, so we have to live with that. So we are given that GM is this. So let's find out this GM. First step, let's find out what is GM. So GM is del ID by del VGS. Differentiate this, you'll get mu C ox W by L. Okay, so this will be into VDS. What is the assumption here? Again, we are assuming this to be ideal. This means long channel. Secondly, that I am assuming it's again not in saturation. I am assuming this. Again, you might ask, why is that so? VDS is 75 millivolts. It's not even 100 millivolts, 0.1 volts which are usually seen. For this small number, I'll assume it's not in saturation. We'll see if we can confirm this. Okay, we'll see if we can confirm this. So let's just proceed with this assumption. So GM was 1.5 milliamps per volt. Mu is something which we don't know. So Cox is something we don't know. W by L is something we don't know. Times VDS. Do we know VDS? Yeah, VDS we know is 75 millivolts. Okay, so this milli and this milli gets cancelled. So what you get is C mu ox W by L is 1.5 over 75 amps per volt square. Okay, we are required to find milliamps, so let's keep this milliamps. Yeah, so let's keep those milliamps, and the Kn is something mu n C ox W over 2L, so which is half of this quantity. So 1.5 over 150 milliamps per volt square. So we do this, and this turns out to be 1.5 over 0.15, because this is shift of decimal. So this is 10 times. So what I'm getting is 10 milliamps per volt square. So is there an option? Yeah, there's an option. 10 milliamps per volt square. Fine. I found out what is the value of this mu n C ox W by L. Now I am more interested in finding out whether I can establish that it's in saturation or not. So I'm thinking along those lines now. So let's see. We know this value, right? Okay. How do I find that? How do I confirm that whether it's in saturation or not? Okay. This term I know, and I know the GM is given to me. The problem is there's no way of knowing what's the value of VGS. just from the GM, the value of GM, because the value of GM does not talk about VGS. So that's the only term that I know. That's the only variable that I know. So in this case, I cannot confirm that, unfortunately, right? But for now, we'll just proceed with this. And yeah, so VDS was 75 millivolts. This is, I guess, this is the only thing with according to which I can have certain confidence that yes, we are indeed in, and we are indeed not in saturation, because VDS is very low. Okay, right. So second part of this problem is that now they are asking the current and VGS equal to 0.8 volts and VDS equal to 1.5 is. Okay, so now this VDS, so this is the first experiment that we did where VDS was 75 millivolts. So this was the first experiment, and we got transconductance parameter. Note, all of these are constant, so this will not change even if we change VDS or VGS, correct? So that was the first thing. Now we are required to find the VGS, current with this VGS and VDS. So again, what I'll do is first we have assumed it to be an ideal MOSFET, assumed ideal and MOSFET. Second thing is we need to find the region of operation. So let's do that. So for that we need to establish that VG is greater than VT, right? So VG is 0.8 volts, should be greater than VT, which is 0.25 volts. So yes, VG is greater than VT. This means we'll have an inversion layer, and then only this expression is valid. Second thing is we'll see VDS and we'll compare it with VDS sat for saturation, that is. So let's do that. VDS is given as 1.5 volts. Now this is the second experiment, correct? Is it greater than VDS sat? VDS sat is nothing but VGS minus VT. So 1.5 volts. Is it greater than VGS? VGS is 0.8 minus VT is, where is VT? VT is 0.25, sorry. So 1.5 is indeed greater than, this comes out to be 0.55 volts. So this is true. This means we are indeed in saturation. Right? So how does this formula change when in saturation? So mu n C ox W by L VGT VDS whole square by 2. You put VDS equal to VDS sat and the rest of the things. So this is VDS sat actually. No wait, sorry, I made a mistake. That's why I don't remember other formula, because I make such mistakes. So it will come out to be VGS whole square by 2. You put VDS equal to VDS sat, which is VGT. So VGT into VGT minus VGT whole square by 2. So only it remains is VGT whole square by 2. So this will become mu n C ox W over TL VGT whole square. This is the term, the Kn that is written. So this is 10. This whole term is 10 times VGT we have determined as 0.55 whole squared. So this turns out to be 10 milliamps times 0.55 squared. So that will be 0.55 squared times 10. So 3.025 milliamps. 3.025 milliamps. So this is per volt square and this is volt square. So volt square get cancelled. So you get milliamps. So the answer has to be rounded off to the nearest integer. So the nearest integer from 3.025 is 3. So GATE actually asks this type of problems where you have to round it off. So just be careful with that, to 1 decimal place, 2 decimal place, because even though you have solved it correctly, just because of a rounding error, you should not lose marks. Right? So again, in this problem, we just figured out from the first experiment, we found out these constants, or the constant in this case. And in the second time, for the second experiment, we have changed the VDS. So when we change the VDS, so our region of operation might change. So what's happening in this problem at least is something like this. Let me use, yeah, no, it's fine. So what's happening in this problem is, So this is ID versus VD. So the first experiment, that's when that is this, when VDS is 75 millivolts, we did it somewhere here. So this is, let's say, VD1 equal to 75 millivolts. The second experiment that we did, which is this is the second experiment. This is the second experiment. Was done when we were in saturation. So we were somewhere here, where VD2 is 1.5 volts. And obviously I'm just assuming that in this case that VG is the same for both, which is not necessarily the case. Okay, VG we cannot establish for the first problem. Okay, so that's how we can, just by changing the VDS, you can change the point of operation from linear to saturation and vice versa. Okay, so now another problem from gate, that is, so we have here is when the gate to source voltage of a MOSFET, threshold voltage is, so VTH is given to us as 400 millivolts, and VGS is given as 900 millivolts. We are in saturation. Okay, and the drain current is 1 milliamps. So we know the drain current is 1 milliamps, right? As neglecting channel with modulation, this is the ideality, the long channel that I have been talking about. Okay, so now, so we have been given, so this is the second, yeah, so we are given VGS1 is 0.9 volts, VT is 0.4 volts, and ID1 is 1 milliamps, and we are given, this is the first experiment, in saturation. Second experiment, again in saturation, where VGS2 has been given as 1.4 volts, and we are required to find ID2. So let me just do this quickly. ID2 over ID1 will be mu n C ox W over 2L. See, in saturation, this formula gets changed to VGT whole square by 2, this whole square bracket. So let me write it, VGT whole square, VGT1 I would say, mu n C ox W over 2L VGT2 whole square. Okay, these terms get cancelled, so what you get is ID2 over ID1 is equal to VGT is VGS1 minus VT, so VGS1 minus VT whole square over VGS2 minus VT whole square. What is VGS1 is VGS2 should come here, this is 2, this is 1. So this is 1.4 volts, 1.4 minus 0.4 whole square divided by 0.9 minus 0.4 whole square. So this is 1 squared over 0.5 squared, this will be 4. So this means ID2 must be 4 times ID1. ID1 is given as 1 milliamps, so the ID2 will turn out to be 4 milliamps. This option. Nothing to do actually here, just the expression is given, you are in saturation. So this term gets simplified to this, you just take the ratio and find out the answer. Alright, so what this illustrates is that if you change VGS, so that's what I've been saying. So we are in saturation, so this is VGS1, this is VGS2, VGS1 and VGS2. So if you increase VGS, you should see an increase in saturation current, which we are seeing here, right? From 1 milliamps, so this was 1 milliamps here, and this is 4 milliamps. Next, this is an important expression. Answer the following is subthreshold swing. So remember, I have been talking about the threshold has been reached. What if it has not been reached? So remember, this is the diagram that we have. The barrier is controlling the flow, right? So this is your source, this is your drain, this is your gate. So barrier is controlling the flow over here, right? If we are not in threshold, this means VG is less than VT. I told you zero inversion layer is not formed, correct? No inversion, but a current can still flow. We call the different names of it, leakage current. In this case, it's driven by thermionic emission. What do I mean? What do I mean by that is that ID will be some constant, let's say I naught, e to the power Vg over kT by q. Okay, this will be of this nature. That's what I mean to say. The drain current will not be 0. So as you can see that it will depend exponentially. It's still very small. Maybe, so ID we are seeing milliamps of current or microamps of current. This will still be nanoamps or picoamps, this whole current. But it depends on VG and exponentially. So ID in linear or saturation, it depends linearly on VG or quadratically, or in fact it's constant in saturation. Here it depends exponentially, right? So there is a term called subthreshold swing, right? So that how we determine that is that how much, the definition of it is that how, if you want to increase the drain current by a factor of 10, by how much you want to change the gate voltage. So let's see, I define ID1 as I naught e to the power VG1 over KT by Q, and ID2 I define it as 10 times ID1. Okay, and this expression would be I naught Vg2 over Kt by Q. So I need to know what should be the difference, how much should Vg2 be different from Vg1 so as to increase by 10 times. Alright, so I just divide these two expressions. So what I get, ID2 by ID1, this is 10. So 10 will be equal to, I naught will get cancelled and we'll get exponential of Vg2 minus Vg1 over Kt by Q. From this you will get delta Vg. The change in Vg that you need to require is Kt by Q ln of 10. Okay, so this is the definition actually. The increase in gate voltage, that, so this is Vg2 minus Vg1. So how much of the gate voltage you should change in order to have one order of increase in the drain current. So remember, if I draw the drain current with this ID versus Vg, is going to be exponential. Thus sometimes we draw it in log scale. So this is linear. So if ID is in log here, right, then it would depend linearly on Vg. So you will see this kind of a plot versus Vg. And there obviously it saturates, so because you are entering the inversion regime or not. Alright, so this is the expression. So the answer would be the increase in drain voltage the increase in gate voltage to increase the drain current by a factor of 10. This is the definition of subthreshold swing. How much you should swing the gate? You should swing the gate, increase in gate voltage, so that drain current increases by a factor of 10. So that's the expression, and we have already known that delta Vg, right, is Kt by Q ln 10, right? So ln 10 into Kt by Q is 26 millivolts, right? So this turns out to be around 60 millivolts. So delta Vg. There are some more complications involved which I'm not going into, but this is the simplest of the explanations because there's actually one more term here, C depletion over C ox, and so I'm not going into that. So the best case that you can do is 60 millivolts, right? Otherwise it will be always, so this is a fundamental event because remember it's Kt by Q. Temperature you cannot change, K and Q you cannot change. I mean temperature you can change, I'm talking about room temperature, so this cannot be breached. So only at 60 millivolts, and this is measured per decade. Why per decade? Because remember we have taken a factor of 10. This is usually called a decade if you remember a Bode plots and everything. So for a factor of, for an order of magnitude change, this means a 10 times change, you must have a subthreshold swing. So I should say it, should not say it something like this. So this is delta Vg, right? Subthreshold swing is given by 60 millivolts per decade. Okay, right? So remember I had said that we always source is at ground and body we also ground. That's not always the case. So it says that source to body must always be greater than or equal to 0 for n MOSFET. Note this is an n plus p junction, and I'm drawing the depletion layer now. It will be something like this. It will be towards the p side because this is n plus, right? So if we somehow, let's say we make it forward bias, this n plus p junction, If we make it forward bias, this means this is grounded, and we apply a positive terminal here, positive here, let's say plus 1 volts. What's going to happen, you will have a PN junction, the current will start conducting from source to body. You don't want that. You want all the current to be here, right? So we call this VBS, body to source, right? This must always be less than 0. This must always be reverse bias or 0. If you don't want reverse bias, just make it as equal to source. So body, source, never forward bias, because then you will start conducting across this PN junction. You don't want that. It must be greater than or equal to 0. No, it must be less than 0, because this is P and N, right? So you must not forward biases. So this is false. You must always reverse biases. Source to substrate PN junction must always be grounded or reverse biased. Yes, that's what I'm saying. It must always be reverse bias. You don't want any current flowing here, at least not for reverse current, some flow, but we know in PN junction it's very small as compared to the current of ID here. Okay, so what we have here is this option. One second. Did I make it wrong? Okay, source to body bias, it's saying, yeah, so this is true. I've said body source never forward bias. Yeah, so body to source, here they're talking about source to body. So yeah, VSB, so VBS should be less than 0. This means VSB, source to body, should always be greater than or equal to 0. Yeah, so that is correct. So 1 is true, 2 is true, and this is the correct explanation. We don't want this forward bias, so this is C is the correct option.